I am Sharath. I'm from Instacart. I will be talking about some of the lessons we learned from how we integrate machine learning models into production, into basically our product. Well, so my experience prior to this, I worked in search and recommendations and ad targeting over the last 10 odd years at various places. Now I lead the search and discovery team at Instacart. It's a product team, sort of cross-functional product team with engineers, designers, data scientists, and analysts. So how many here have heard of Instacart before Ian just mentioned? Okay, and how many have placed an order? Okay, how many of you got really a bad replacement, like a cucumber with a zucchini? That's probably my mistake. Sorry about that. So Instacart is an on-demand grocery delivery service. So essentially, we don't have warehouses. We deliver from stores that you already know that you would otherwise shop from. And there's a customer app. You select a store, you add groceries, you place an order, and that could get to your place in as little as an hour. My personal record is like 37 minutes. It's kind of amazing. There's a shopper app, which is an entirely different thing. And this is a case where people sign up to be shoppers. They walk into the store, and they're scheduled to be in the store at a certain time based on how we can estimate demand from that store, at that hour. And so they're already in the store. They accept your order. They shop for your items. And they potentially communicate with you through the app if they have a clarification, and then they deliver it at your door. Right? So that's sort of the model. And if you think about the players here, there are customers, people placing orders, there are shoppers, those in the store. Then there are the retailers themselves, like Whole Foods and Safeways of the world, and then there are the advertisers or product. People who basically build the product. When I say product, I mean, well, things like a box of cereal, right? So brands, rather. So these are the four players. There is like a four-sided marketplace. And any of these interactions between any of these players is sort of ripe for an opportunity to build a data product, right? Matching, there are multiple workflows for each of these players, and there are places you can optimize. So there are plenty of different problems to work on. So that's just the context so that we can move into like what I'm talking about in terms of more general experience based on what we saw there, right? So you could imagine that in the beginning there was, if you think about when you start off a company, you probably are solving the most important problem for the customer. You're doing it anyway, but even say within data scientists or in the data science team, you're picking one problem, trying to solve that in the easiest possible way. So think about how that architecture is going to be. You probably have like one production database for pretty much everything, and you're pulling data from that, you're creating your training data, you're building a model, and you're writing the model back to your database, either a location of a file or the model itself. If it's a bunch of coefficients, you're running it in the database, right? So that's literally the first ever sort of training pipeline. And then the test pipeline, or scoring pipeline, is essentially sort of similar. You do pretty much the exact same thing, except instead of training the model, you are scoring examples. And you write back your predictions to the database, and you use them. Or maybe you score it in real time, which also happens, but probably not often the case. So what you have here is a very simple case where like the training and the scoring is essentially identical, right? The same code path, and so it's kind of low risk. But you can't do that forever, and you can't do that. Well, you can do that as long as you have like one problem and scale is not an issue, or there's no microservices that you need to worry about. All you have to do is just write to the database and read from the database. Right? It's simple architecture, and SLAs are not a thing either. Right? So that's probably the first ever thing that somebody builds. But But eventually, though, models get, like, the product gets more complicated, right? You get product market fit, you have scale, you can't, SLAs matter, and, you can't imagine there's so many things happening in the app, and there's one model that you have. You can't afford to bring down the entire app because of that one model, right? And so things that work when you have one model doesn't work when you move on to other models. And so what you get is you got to find a way to think about, okay, how do I now change the way machine learning is done when I go from one model to more models? And these are sort of the issues that we've experienced. And just as an example, going over a few different things that we do, right? So you land on the storefront, you open an app, basically you load the app up, or you're on the web, you land on the storefront. As Instacart, we personalize your experience on the site, which means what sort of departments to show, what products to show, what ranking do they appear. As you can imagine, grocery is very different from regular e-commerce, where in groceries, there's a thing about buying things over and over again. So there's a combination of recurring orders, and then there's also discovery, right? So how do you balance these two? How do you present products and product categories on your storefront? That is one problem. Another one, which I guess every site has, is search. How do you rank search products in response to a query? Another one might be, like I mentioned, replacements. One unique thing about the way we do on-demand delivery is we are picking from stores that are not our inventory, right? These are not our warehouses. And also, these are stores where anybody else is going and picking the same things from. So if, let's say you place an order, for a bag of chips to be delivered tomorrow evening, when the shopper goes to the store, we don't know if those bag of chips will actually be there for sure, right? There is a chance it's not there, and we want to prepare the customers for it. So one problem is, how do you recommend substitute products for the customer, right? The other is, well, a typical grocery, think of a family of 4, right? And easily somebody's ordering weekly is probably adding like a couple of dozen things to their cart. So how fast you can keep the shopping going matters. Otherwise, you're going to have, like, think about if you have to add 24 things to the cart and you have to evaluate at least 2 things before you add one, you're essentially spending easily over an hour building your cart, which is sort of very unusual, right? So speeding that up, which means like recommending the next thing that you might be interested in. If you add a bag of chips, we probably recommend you salsa. But if you bought salsa, a last order, we probably don't want to do that, right? So recommending the next item is another problem. So now these are experiences that are sort of peppered throughout the product, and each of these things are complex. And how do you integrate that without hurting the core user experience? These are some of the problems that we've had to work with. So what that means is it changes how we go from one model to like probably a couple of dozen different data products, right? So one thing we try to look at when evaluating how should a model be integrated into a customer workflow is think of like the response time. Latency, response times. What can people tolerate for this particular experience? And that's really depend on the product itself. It certainly depends on customers. I'm sure some people are more impatient than others, but generally at a product level, think about, let's say, web search. Web search people essentially expect like sub-second latency. But think about travel search, right? People easily sort of tolerate more than 5-10 seconds. And I don't know in the last 10 years if travel search has gotten any faster. It's almost like customers are anchored to that experience. And if you're building a search engine optimization or search engine ranking at a travel search company, you're better off investing any latency benefits into improving the ranking itself. Because you know that people, just because you make it 4.5 seconds, maybe people don't actually care that much. But there are other places, let's say evaluating loan applications, where it might take even more. You may wait like half a minute before you're told, okay, this is your interest rate, you're accepted or otherwise, right? So in general, I feel like what we've seen, like if there is a high payoff, and if there's a one-off interaction, then you can afford more delays compared to if it's like several, page loads before you do something. Right? So building a cart has to be really fast, right? So that's the latency aspect, right? The second thing is context sensitivity. So the question then is like, how much information do you need to make that decision? How much context do you need? How much does more recent data matter? Right? And you could think of extremes where every single input is independent of the other input. Let's say you're doing, think about this problem where we are ingesting data from retailers, and we have to look at a product. If it's in the catalog, fine, great. We get it already gets matched to something that's already there. But if it's not, then you're matching. You probably have to do a bunch of things like, okay, what category does this product belong to? Right? It's a hypothetical example, right? So this is not that context sensitive. You look at a document, you have to make like a text categorization decision. This is like produce, or this is like shampoo, so on, right? So some problems don't benefit from context. So if you think about like how much do you benefit from more recent data, that's like one more place that really changes the way the models interact with your product and how you architect your model itself. So one sort of clever thing you can do is change the product experience so that you sort of buy more time to score. Let's say you need to score, you need more data to score, ask more important information first. Keep predicting in the background, like what's your best guess, so that you're always ready to present that decision. So there are ways to sort of buy time to get more context, right? So there's the latency, and then there's context sensitivity. And if you put that in a quadrant, which you would see, essentially you would have 4 different combinations with low latency, highly context sensitive, and the other 3 combinations. And one question we ask is like, where does what we want to do belong, right? Think of this example where if something is a very low latency requirement and it is context sensitive, an example might be search ranking, where you really cannot cache. Things have to be really fast, sub-second. It benefits from more recent data. So that could be one example, really strict SLAs. The other extreme is like our first example. Like, latency is not a big deal, and there's no context sensitivity, right? These are like a lot of classic recommendation systems where you're training on like several months of user behavior, and you're scoring essentially in the same pipeline, instantaneous scoring. And you can score it, and you can cache it, and you can serve it. So assuming the serving latency is not very high. But scoring could be as high as you want, because it really doesn't matter. There's no context, right? So that gives you like these 2 extremes, right? And then, well, the other 2, which is low latency and no context required. And we've seen this, for example, with, think about this. Think about like the customer expects things to be really fast, but the decision can be made without a lot of past data. This is a case with, say, when you have a long tail of inputs, and inputs are sort of unpredictable, and you cannot really cache except in the head, but the tail is long, right? But it has to be fast. So that one example would be, in our experience, like if you're ranking search, the first level of matching for search, the TF-IDF or BM25, like simple elastic search calls, that sort of fall in this category. And we have some of those as well. And finally, my favorite is when latency is, well, it's context sensitive, but latency isn't such a big deal. And that is where, the early example, like, imagine that you're building your cart, you're adding potentially 10 things to your cart. And each time you add things to the cart, there's something in the background that is scoring, for some outcome. It keeps scoring. It always keeps a best estimate of, whatever it's trying to estimate. Maybe it's, what should I recommend you at checkout? Some impulse purchase, making up an example. And it's doing that all the time, right? And whenever you ask for a response, you get it, right? So this is where the latency of scoring doesn't matter because the scoring is happening in the background. But the context matters because, well, context helps for that task. So you want to use as much data as possible. In the extreme case, you might think, well, everything has to be like low latency and context sensitive, right? That's where you consider all the data you have or you can get, and everything is super fast. Right? But everything doesn't have to be that way, right? So in our case, for example, so the question we ask is, well, you want to be in sort of the first quadrant. You want to be low latency, context sensitive, but can you start somewhere else? Because that's probably the hardest place to be. So can you start by being in low latency, reasonable latency and no context? So you start from, let's say, quadrant 3 in that case, right? And which means that you're doing as much as possible in batch mode and you're caching things. Can you start there and then can you move to high context and reasonable latency, sort of quadrant 2? And then eventually you get to quadrant 1, right? Where does your problem belong and where does it eventually need to be from the customer point of view, and where can you start, right? So recommendation is an example where you can start off with reasonably good recommendations by just batch scoring in the in a batch mode. So that simplifies how you do training and how you do scoring. You can then move to scoring in the background with context, but latency is still you're still willing to live with latency because you're scoring in the background based on most recent information. So you go from quadrant 3 to 2 and you land up in 1. Right? For some problems, you can't be in quadrant 3 at all because you can't actually have a high latency solution for that. So you might actually start in quadrant 4 where the simplest thing is, well, you respect the latency, but you don't really necessarily use a lot of context, and see what you can score with that. So start from Q4 and then you move towards the ideal place for that problem, which is low latency and high context. And this sort of assert as well, where we start off a data product in a place that we can, the goal for us very often is to set up that workflow both on the back end, on the front end. These are discussions that we have with data engineers because it has implications for logging and aggregations. And also discussions we have with product engineers because they are the ones that are consuming our output. And very often they would push for, it's a sort of a tension, like we want the models to be as accurate as possible, but we don't want to stress other parts of either the infrastructure or other parts of the consumer experience. Right? So this sort of framework helps us think about where we want to be or where we want to start and how do we eventually get to quadrant 1, if that makes sense. Okay, so the second thing that we saw, which is essentially outside of one level sort of deeper, is you have one model, that's where you've been for a while. Now you have product market fit and scale. There are more opportunities where AI or machine learning matters, predictive modeling matters, and so now we have more models. There are more models, more features, more people building them, and more people duplicating things, right? So what I like to think of is there something, we talk about like economies of scale, where as you buy or as you work on larger scales, things become either more cost effective or easier to do. There's also the economies of scope, which is, it's not so much about like how many things you do, but how many different things you do. If you have like 7, 8 different models that are doing somewhat related things, when I say related, they probably share a good part of the inputs. So for any consumer product, say a user profile is something that's shared by, something that benefits many models and many tasks, right? So user profiles are things that everybody wants, and everybody has essentially their own view of what those profiles should look like. How should you encode a certain feature, right? Or product profiles, product attributes, product taxonomy related attributes. So that might be like, what is the average popularity of this product in the last N weeks? So these are features that are useful for any number of models that we might build, and we realize we have to find a way to share features across models, right? And we want to do that in a way that doesn't get in the way of like productivity. If anything, it helps iterate faster. And it is also sort of aligned with transfer learning, wherein you learn features in a particular problem, and you're able to translate that, use those features in a related data set, prediction problem. So think about, let's say, to specific examples. If you're trying to find a replacement, we've talked about this problem before. What's a good replacement for a product X? And what you're trying to think of, like, what kind of features matter? Some kind of match between the product description. That matters, certainly. The price difference matters. Is it the same brand? Is it organic? Or rather, are they both organic? Are they both the same brand? That sort of stuff matters. Also, some kind of affinity, right? Even independent of the source product, how much does a particular user, the personalization component, how much does a user like this particular brand? That matters, right? Now think about a different problem like ranking products for a particular query for a particular user. Obviously, the match between the query and the product matters. And how often that user has bought that product before, that matters. But also that same affinity that we talked about. How much does this person like products like these, even if they haven't bought them before, right? So that's an example of a feature that matters in two different problems. Because really, we're thinking about like entities. Our entities are queries, brands, customers, products in the entire catalog hierarchy. Any sort of data problem we take is some sort of relationship between these two, right? If you're trying to do ad targeting, you're trying to match users and brands. If you're trying to do personalization, you're matching users and products. If you're doing related products, it's a pair of products. If you're trying to do spell correction, it's a pair of queries, right? So there are a lot of opportunities for like sharing features across models. And one thing that we came up with is, if you think of the features themselves, there's some on-the-fly features that that just have to be computed. Is the item on sale right now? You can't cache that, right? It just comes as an attribute of the product. There's no need to do anything special at scoring time. It's available to all the models on an equal footing. And then there are these aggregate features. Features like, how often did this user buy this brand product, in the last few months? Or how often do people type in avocado and buy, something from personal care, like avocado flavored shampoo or soap or something, right? More likely they buy something from produce. So these sort of aggregate features, right? And then there are features that are like learned features, learned representations that come from, deep models, or shallow models like word2vec, or not even neural networks like LDA vectors that you can compute for a user. You can have that being computed in a pipeline, and you can just have them used across models. Nobody needs to think about recomputing these features, right? So these three categories of features, and the last two you can cache, or rather you can have a centralized key value store that allows us to use these features across models. And that's basically what we did. So what does this sort of key value store need to do? Think about it as, I know that for a given model, I need to know that these are the list of features I need. I need the LDA vectors for a user. I need the LDA vectors for product, word2vec vectors for a user, product, and so on. I need aggregate features for users. How often did a user buy a certain product? So you only need to say what you need for a model, and you should just assume that you'll get it. You'll get it at training time. You'll get it at scoring time. because you know that somebody is writing to it, writing those features to the key value store, right? So what this allows us to do is not just share features, but also sort of maintain the sort of sacred contract, which is, if you see an observation, and if you extract features for that in training, it should be the exact same as if you extract features in scoring time. That's something that is sort of non-negotiable with like feature extraction, right? But now, since you're reading features from the same key value store, that is automatically guaranteed. And there are other ways of doing it, right? We could think of, you can log features at training, at scoring. Because you're scoring and you're computing features, you can log them, right? And then you can use the same features at training time. So that's like one more way, and probably arguably the most robust way, because you know exactly what the feature was when it was computed and scored. But you had to be careful that this will not work if you have new features. You want to try new features, you have to recompute them in your training pipeline. Right? So two things basically are achieved. We are able to share features, and we're able to maintain the sort of sacred contract of feature extraction. Right? And just a very little bit about what that one more level of detail, right? So what do you need? You need like a highly available key value store, like Cassandra or Dynamo, that essentially takes, it only knows that my key is a user product. My value is this giant vector. The key name has some semantics about what that feature is, right? And how you extract feature, or rather how do you read features, is something that the library takes care for you, right? Because all it needs to do is, think about like you need to be able to say that this is a feature that I want, and the model, when you specify the model at scoring time, it has all the feature names, and it parses that to understand that these are shared features. It is able to then extract these features from the key value store and then stitch them together in a data frame, which is now, you can combine that with other features that you're doing. So all you had to think about is, for this model, what are the unique features that are specific to this model, and what are the features that are shared features? And that significantly simplifies whatever the task is. So now you have a simple example is you have features to compute a replacement for a product. Now imagine you have another task where I need to compute, let's say, is this product a new version of the other product, or a size variant of the other product, which is useful? You could pretty much run with the same features and a few extra features, and you're able to spin up a model. So that's that's a pattern that we've seen. And we have this running right now in production for like 3 different models, with sort of in a sort of similar task that have like fair amount of shared features, and that's worked well. So that's what I have.